Hey there, welcome back to CMTEQ channel. In this tutorial, we're diving into a classic power system problem involving per unit system and short circuit calculation. We are basically tasked to calculate the required reactor reactance to limit the short circuit MVA to 550 megavolt ampere for a fault at F in a ring connected system, as you can see here. This is tutorial 13 on our series of short circuit MVA calculation. So without any further ado, let's get right into it. Great. Now moving on, as we can see here, we are given a ring system, basically reactors connected in a ring system that basically form a delta configuration. And our goal here is to find the missing reactance here so that we can find the fault here at this location, which is actually already given to us here, to 550 MVA. So this basically means you have to find these reactance here that will limit the fault at exactly this value. So to do that, obviously you need to convert this system into a per unit equivalent impedance diagram that will now enable you to find the total fault impedance, because the point here is to find the total fault impedance leading to this fault location. Once you know that, you can find the short circuit current and you are assured to find the short circuit MVA. So how are we going to proceed? First thing first, we need to find the per unit impedance of each one of these generators that are connected in a delta configuration with these reactors. So to find the per unit, we use this general per unit formula, Z per unit new, right? Because these generators here are said to have a 20% per unit reactance each, but that is the old one. But since we are going to be working on a new system, a new base system with a 50 MVA base that we're going to assume, so we need to convert every parameter into a new base MVA. So to do that, this is the formula that you have to make use of. So that is Z per unit new is equal to Z per unit old, that is the given per unit reactance here, times SB new will be the new assumed base MVA. SB old will be the old base MVA for each one of these generator is equal to 50 MVA, and that must be multiplied by VB old over VB new close bracket square. Now VB old and VB new becomes very crucial if you have systems that include transformers, because as you move from transformers stepping down or stepping up to a different voltage level, your base voltage changes. This is why you must take account of VB old and VB new. But in our systems here, we don't have any transformers in the system. We only have these generators here. So which means in our case here, 33 kilovolt will basically be VB old and VB new, as these are the voltage for our line and the voltage that these generators are basically generating. So having said that, we can then go ahead and calculate the first per unit for generator A. That will be equal to 0.2 J per unit. For generator B, that will be 0.2 J per unit, and the same for generator C. Now if you want to know more about how we arrive at this answer, obviously by following the formulas, I've got plenty of tutorial on per unit tutorial. Please watch that playlist. Cover different type of exercise or examples that will set you on the right path in terms of per unit system calculations. Now we're moving forward to calculate the total per unit impedance. We obviously need to convert this system into a star, because it is a balanced delta system that must be converted into a star configuration so that we can be able to reduce our network to lead us to the fault impedance that we are looking for. Great. Now we can go ahead and rearrange our ring system to represent a proper delta system. Okay, so this is our delta configuration. Okay, now after converting into a star, we then going to have this reactor here in series with ZA here, and that will basically be for generator A, and generator B reactor will be in series with ZB, and so forth. Now to convert this delta into a star configuration is very simple for a balanced system, because they say here reactors are identical. Since the reactors are identical, that means this X and this X and this X are basically equal in our delta configuration. That means it's a balanced system. So the conversion becomes very simple. By the way, if you find this tutorial useful, please make sure you give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. Now moving on, we basically going to use a simple conversion formula. Since it is a balanced system, ZA is equal to ZB is equal to ZC, and that is equal to XAB divided by 3 equal to XBC divided by 3 equal to XCA divided by 3, right? So that basically means this point here is A, and this point is B, and this point is C. So we basically are saying here that the impedance between this point must be divided by 3. The impedance between this point must be divided by 3, and so forth. And the result will be the star configurations of our network. But in a case where this was not a balanced system, let's say it was unbalanced, okay? So in that case, you're going to use this formula here, where your ZA must then be equal to the reactance between AC times AB divided by the sums of all the reactants in a delta configuration, and ZB will be ZAB times ZBC divided by the sum. That's basically how you going to solve it. Now moving on, we now know that our reactance here, ZA, ZB, and ZC are all equal, and it is equal to X over 3, because we know that XCA and XBC and XAB is nothing but X, right? So it is in percentage, so it's X. It's a reactance. We don't know what it is, so we just say it's X divided by 3. So now we are all set now to redraw our new configuration, which is now a star configuration. So that basically what we're going to get here. And as you can see here, we've got GA with the series reactance and the new star conversion, GC which is series reactance and the conversion, and so forth. Now this become a very simple system for us to convert and find the total per unit impedance that will lead us to where we are going, and help us find the fault current that will help us find the fault MVA. Now let's go ahead and reduce our star configuration into a simple series parallel configuration. So let's go ahead. Now from here we can clearly see that GA and GB, they are in parallel leading to this point, okay? And the current being delivered by GA and GB will flow down to this point here, leading to the fault location. Okay, so we can redraw this to say GA and GB clearly in parallel to something like this. Okay, so this is our fault location, and this is the center point of our star, and this is GA and GB, they basically in parallel. So we've got this reactance here plus X over 3, and this reactance plus X over 3. So our goal here now is to work out these parallel configuration. So to do that, it's very simple algebraic manipulations. So we're going to have GA and GB in parallel, will basically give you this expression here, okay? And that can be reduced to this expression, and calculating it further, reduction, we're going to have this expression divided by this expression, and that will lead you to this expression. And obviously you can further reduce this by multiplying the 3 into the bracket here, okay, and that will give you this expression that can be reduced to this expression. And finally, the parallel configuration of GA and GB will give you 0.1 plus X over 6. this is a simple algebraic manipulation you're doing here, but you have to be very careful, because if you get a wrong answer here, that means you're not going to find the correct value of x. If you don't find the correct value of x, you're not going to find the correct value of the short circuit current. That basically means you won't be able to find the 550 MVA that is required for these percentage reactance to be set at a specific value. So you have to be very careful, right, on these calculations. But now there is an alternative method to the way of solving this parallel branch here, and that is simply by setting 1 over the sum of basically the two branches here, 0.2 plus x over 3 plus 0.2 plus x over 3, and from here you can basically invert your equations and calculate the sum. So if you have something like this, basically it's a common denominator that we've got here. So you're going to have 1 plus 1 is 2 with a common denominator, and once you've got it like this, you can invert it back, okay, and that will give you something like this, and you can further simplify it, and you're gonna have 0.1 plus x over 6 now. And once you have it in this form, you can further invert it back to the previous form. So that will be 0.2 plus x over 3 divided by 2. And by simplifying, you basically going to find the same expression here, which is 0.1 plus x over 6. It is exactly the same expression. Great. Now from here, we can now draw our new drawing with a reduced parallel branch here of GA and GB that are now being reduced to 0.1 plus x over 6, and that will basically give us the following drawing. Now remember this point here, okay, this was this point here, and this is still our star point. Now obviously this and this are in series, so you can just combine the two of them. So that will just give you x over 3 plus 0.1 plus x over 6, and that will give you 0.1 plus 9x over 18. You can further simplify this to 0.1 plus x over 2 or 0.1 plus 0.5x. Basically this is 1 over 2, so you can divide 1 by 2 to have 0.5. And our new drawing again is now going to be just GC here, generator GC, and this is our fault location, okay, and now we now going to have 0.1 plus 0.5x coming from the parallel configuration of GA and GB. Now the value of x over 3 here after the fault have already been combined with the parallel configuration. That's why we have the fault location here and generator C right here. Now these two parameters are now also in parallel, leading to the fault location. Great. Now before we wrap up this tutorial part 1, I'd like to say that if you are busy studying your electrical engineering degree and you'd like to receive assistance from CMTEQ channel, please do not hesitate to reach out. Join the channel membership. I will be more than happy to provide assistance where I can. Thank you so very much. Now we can further reduce this parallel branch here leading to the fault by simply working it out, GC parallel to GA GB in a very simplistic algebraic way, and that will give you this expression 0,02 plus 0,1 x over 0.3 plus 0.x5. Now this is expression for Z per unit total, okay, but we still have an unknown variable here, x, that we need to find so that we can know what will be the Z per unit total leading to this fault. Now I'm going to stop the tutorial here. Please make sure you join in and turn in on part 2 2 of this tutorial, where we're going to basically solve the remaining part of the classic power system problem. But if you've been following all my tutorial, from here you apply your mind, you should be able to find the solution. And let me know on the comment section below if you have found the solution before I post the next part of this tutorial. Until next time, if you find this tutorial useful, please don't forget to give it a thumbs up, share it to your social media network. That will be highly appreciated. Until next time, cheers.